Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is DC math. Our objective is to review basic math skills encountered during the Basic Electrical Circuit Analysis series. We'll review negative and fractional exponents, the order of operations, and the scientific calculator. Note my dramatic overemphasis of the term review. This lecture operates under the presumption you have a prior background and general familiarity with math, or at the very least, a non-adversarial relationship with numbers. Bottom line up front, this is not a math class, and I refuse to teach you math. This is a circuit analysis class, and it uses math to predict and interpret electrical theory. This lecture's only intention is to clean up, organize, and put a sharp edge on common math tools you may or may not have used in some time. This lecture additionally operates under the assumption the viewer is skilled at writing and reading numbers in proper engineering format and can enter and interpret numbers expressed in engineering format in the scientific calculator, as illustrated in the engineering prefixes and exponential format engineering lectures, both available at the Big Bad Tech channel. If you haven't watched these lectures yet, only dim and recall their contents, please take the time to do so now. Let's start with a quick review of negative and fractional exponents. A negative exponent is when a base is raised to a negative power, as in 10 to the negative third. The negative sign means the base 10 is on the bottom side of the fraction, the denominator, in this case 1 over 10. Then the base is raised to this power, in this case 3. 10 to the third is 10 times 10 times 10, or 1,000, so the expression 10 to the negative third is 1 over 10 to the third, or 1 over 1,000, or in decimal form 0.001. Another example of negative exponentiation is 2 to the negative 4. This is asking us to move 2 to the denominator side of a fraction and then raise it to the power of 4. 2 to the fourth is 16, so 2 to the negative fourth is 1 over 16, or the decimal equivalent, 0.0625. Moving on. Let's now take a look at fractional exponents. A fractional exponent is the same thing as a root. 81 raised to the half is equivalent to square root of 81. Both these expressions are asking to solve what number multiplied by itself yields 81. In this case, 9. Lacking a superscript, the square root is implied. But if you want to be specific, you could place a tiny superscript 2 in front of the root operation. Another example of fractional exponents is 64 raised to the third power. This means solve for the cubic root of 64. Both these expressions are ultimately asking what number multiplied by itself 3 times yields 64. Both of these expressions yield a result of 4 because 4 times 4 times 4 equals 64. Let us now begin with a review of the order of operations and the scientific calculator. Whereas the review of negative and fractional exponents went rather quickly, expect this one to take some time. Consider the expression 2 plus 4 times 8. Given my flat affect, it's hard to tell if I meant 2 plus 4 times 8 or 2 plus 4 times 8. If I was to write the expression out without any indication of sequence, those individuals with differing level of familiarity with the order of operations might arrive at one of two answers, either 34 or 48, only one of which is correct. Take a guess. 5, 4, 3, 2, dramatic pause, 1. As presently illustrated, the correct answer is 34, because the order of operations places a higher precedence on multiplication than it does addition. Allow me to demonstrate. The order of operations establishes clear and consistent rules regarding the calculation of numerical quantities. It establishes a recognized hierarchy of mathematical operators, and the hierarchy is rigidly adhered to at all times by all people and all machines. This hierarchy is often illustrated using the acronym PEMDAS, where PEMDAS means parentheses, exponentiation, meaning powers and roots, multiplication and division, and addition and subtraction. Note multiplication and division and addition and subtraction occupy the same levels of the hierarchy, meaning these operations occur simultaneously. We'll explore the significance in a series of illustrated example problems later. If we were to apply the order of operations to our original expression, 2 plus 4 times 8, we need to walk through each level of the order of operations in the specified sequence. Parentheses are at the top of the heap, and any operation inside parentheses receives priority. There are no parentheses in this particular expression, so we're free to move down one level in the hierarchy. The next level in the order of operations is exponentiation. Nothing's being raised to any power, nor are we being asked to solve for any roots. We're again free to move down one level in the hierarchy. The next level in the order of operations is multiplication and division. our expression has a multiplication operator between 4 and 8. Multiplication receives priority. 4 times 8 equals 32. We're now at the bottom floor of the order of operations. We find addition and subtraction. We can now freely add 2 and 32. The undebatable answer to the expression 2 plus 4 times 8, as dictated by the order of operations, is 34. Note, if you wanted to, you can take the step of enclosing 4 times 8 in parentheses to make it excruciatingly clear that multiplication comes first, but it's not absolutely necessary, given multiplication and division precede addition and subtraction anyways, as specified by the order of operations. This being said, if you got a couple extra parentheses hanging around, not doing anything useful, feel free to put them to work. What if we really did want to add 2 plus 4 first, and then multiply the summation by 8? This is a totally different expression and will yield a totally different result. If this is our intention, we must then explicitly state the specified sequence by enclosing 2 plus 4 inside parentheses. Applying the order of operations hierarchy to this new expression, we're first asked to solve for operations inside the parentheses. 2 plus 4 equals 6. Now we move down the hierarchy. There are no powers nor roots. Move down one level. There is a multiplication operator. 6 times 8 equals 48. There are no further operations. This is the final answer. Note the inclusion of parentheses makes it readily apparent that the addition of 2 and 4 is to come before multiplication by 8. Again, this is a fundamentally different expression than our first example and yields a totally different result, as one might expect. Before we move on to some illustrated examples, I'd like to show you how I'm entering expressions into the TI-89 scientific calculator and interpreting the results. If you set up your calculator as requested in the aforementioned lectures, the mode pages should look like this. Page F1, display digits, float, angle, degree, exponential format, engineering, and complex format, polar. Page F2, exact versus approximate should be approximate, and your base should be decimal. Of interest to today's lecture, display digits float enables the calculator to display all relevant decimal places, and a user is free to round to the desired degree of accuracy. Exponential format engineering makes the calculator display all results in engineering format using the coefficient times the power of 10. The exponential format engineering lecture, available at the Big Bad Tech channel, dealt extensively with this topic. Lastly, approximate enables the calculator to display all fractions and irrational numbers as decimal equivalents. Provided your calculator is set up as requested, we now need to learn how to enter expressions properly. Perhaps the single most important piece of advice I could give to you is this. The calculator does what you tell it to do. The calculator always follows the order of operations, and if you want to impose precedence on particular operations, you must make the calculator aware of this fact. Allow me to demonstrate. Consider the original expression 2 plus 4 times 8. Enter it as 2 plus 4 times 8. Press enter. As we might expect, the calculator applies the order of operations such that the multiplication receives higher priority than addition and returns a value of 34. Notice the calculator takes the time to rewrite the expression on the left-hand side. This is a great way of checking your work. Did you mean to enter this expression as indicated? If so, move on to the next problem. If not, the calculator is not at fault. It's doing its job by applying the order of operations as directed to the expression you entered. Your job is to figure out how to enter the expression such that the desired sequence is executed properly. In this case, this is exactly what we wanted to do, and this is the correct answer. Consider a different expression. Parentheses, 2 plus 4, parentheses, times 8. The addition operation inside the parentheses indicates that this operation is to have precedence. If we wanted to enter this particular expression into the calculator, we enter it as left parentheses, 2 plus 4, right parentheses, times 8. As we might expect, the calculator applies the order of operations such that the addition operation inside the parentheses receives a higher priority than multiplication and returns a value of 48. Again, notice the calculator takes the time to rewrite the expression on the left-hand side. Did you mean to enter this expression as indicated? If so, move on to the next problem. If not, figure it out. In this case, this is exactly what we wanted to do, and this is the correct answer. While we're on the subject of entering expressions into scientific calculators and interpreting the results, allow me to demonstrate another handy feature available on most scientific calculators, the previous results key, by way of an illustrated example. Consider the expression 200 divided by 200 plus 400 times 12. This expression might seem pretty simple, but trust me, it's a trap for those unversed in the use of the scientific calculator. Watch me trigger the trap. Order of operations be damned, just enter the expression left to right with no indication of sequence. 200 divided by 200 plus 400 times 12. Press enter. The trap is sprung. The calculator returns 4.801E3, meaning 4.801 times 10 to the third or 1,000. Expressed using a base unit, let's pretend it's volts. This would be 4,801 volts. In proper engineering format, rounded to the tens place, we might express this as roughly 4.8 kilovolts. This is not the answer because it's not the intended expression. Again, notice the calculator takes the time to rewrite the as entered expression on the left-hand side. Did you mean to enter this particular expression? No, but that is indeed what you fed it. The calculator simply applied the order operations to the as entered expression of 200 divided by 200 plus 400 times 12. There are no parentheses, nor is there any exponentiation, therefore multiplication and division receive priority. 200 divided by 200 equals 1, and 400 times 12 equals 4,800. Move down one level. Addition. 1 plus 4,800 equals 4,801. This is the answer to the expression we entered, but it's not the expression we wanted. How do we enter the expression 200 divided by 200 plus 400 times 12? Consider the original expression as illustrated. Apply the order of operations. There's no parentheses, so we move down one level in the order of operations, right? Wrong. This might take some practice and repeat exposure, but I'm asking you to slow down and really look how the expression is written. The entire operation, 200 plus 400, is below the division line, i.e. in the denominator. To make this exceedingly clear, one could take the trouble to enclose 200 plus 400 in parentheses. If you step back and take a more holistic look at this, one might think of 200 divided by 200 plus 400 as a ratio times 12, or some fraction of 12. One could make this exceedingly clear with yet another set of parentheses enclosing the ratio. Parentheses inside parentheses. This means perform the operations inside to out. We are now clearly directed to solve 200 plus 400, which equals 600. We then divide 200 by 600, being 1/3 or 0.333 in decimal form, times 12 for a final answer of 4. This is the correct answer as dictated by the order of operations. Now, how do we feed the calculator this exact expression? There's two methods. Actually, there's a bunch of methods, but I'm going to highlight two. Method 1, use parentheses. Use as many parentheses as you want to make it exceedingly clear the desired sequence of operations. Some of these parentheses might be an overkill, but who cares? The more explicit your directions are, the less chance of error. Here's one way to write this expression in one line. Parentheses 200 divided by parentheses 200 plus 400 parentheses times 12, press enter. The calculator returns 4 as we expect. Again, notice the calculator takes the time to rewrite the expression on the left-hand side. Did you mean to enter this expression as indicated? Indeed, we did. This looks exactly like our expression of interest. Method 2, use previous results. Sometimes it's impractical to write a large expression in one line using parentheses, and instead of feeding the calculator the whole expression at once, feed it a little bit at a time. Consider the original expression. The way it's written, we need to resolve the addition operation in the denominator first. 200 plus 400, press enter. The calculator returns 600 as we might expect. Now we need to divide 200 by 600. 200 divided by, don't you dare retype 600. It's a waste of your time and you might screw it up if you ever had to enter a more complicated number. Simply use the previous results key by pressing second answer in the bottom right corner. Press enter. The calculator gives us the decimal equivalent for 1/3 expressed in engineering format. Now we need to multiply this by 12. Again, don't you dare manually re-enter this data. It's a waste of your time. Simply use the previous results. either second answer times 12, or just start with times 12, and the calculator immediately goes up and grabs the previous results and inserts them in front of the multiplication operator. Press enter. The calculator returns 4 as we might expect. Again, your choice, either the judicious use of parentheses to pack a larger expression onto a single line, or chop the larger expression into smaller bits and use the previous results. I tend to use the previous results method since it's quicker. This being said, if you use parentheses properly, there's an opportunity to check your work given the calculator rewrites the as-entered expression on the left-hand side. You'd think I'd cut you loose on some illustrated examples by now, but there's much, much more to be said about previous results. Trust me, I'm going to come back and hammer this point at the close of this lecture. Keep in mind, previous results aren't just limited to the prior calculation. Any result or entry in the calculator's scrolling history can be used in later expressions, even if you've last touched those results hours or even days ago. As long as you haven't cleared the calculator's memory, they're there for the taking. Consider the expression 330 times 470 divided by 330 plus 470. Note the addition operator is entirely below the denominator. Yeah, you can try to enter this using a bunch of parentheses, but you can also use the previous results key. My method is to compartmentalize this as a numerator and a denominator. Perform the numerator operation first. 330 times 470, press enter. Forget about it. Now do the denominator operation. 330 plus 470, press enter. Forget about it. All you got to do now is divide the numerator by the denominator. Don't you dare re-enter these numbers. It's a waste of your time and you're going to screw it up. They're already in the calculator in the most accurate form. Just go get them. Use the arrow keys to walk up, and then grab the result of the numerator operation. Press enter. Divided by, use the arrow keys to walk up and grab the result of the denominator operation. Press enter. Press enter again. The calculator yields a result of 193.875. If we round this to the tens place, our final answer would be 193.9. Alright, I do believe I've given you enough guidance on the order of operations, the use of the parentheses, and previous results of the scientific calculator to put your understanding of these concepts to a test with a set of illustrated examples. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. A number of these problems feature the same number and the same operators, yet parentheses or arrangement significantly affects the sequence of operations. We're first being asked to solve for 2 times 5 squared minus 3. Exponentiation receives priority. 5 squared is 25. Then multiplication receives priority. 2 times 25 is 50. We're then left to solve for 50 minus 3, which yields a final result of 47. Next problem asks us to solve for 2 times parentheses 5 squared minus 3 parentheses. We need to resolve those operations inside the parentheses first. Inside the parentheses, we're presented with another exponentiation. 5 squared is 25. Again, we're still inside the parentheses, so we need to resolve this operation. 25 minus 3 is 22. We're now free to multiply 2 times 22 for a final result of 44. Our next problem asks us to solve for 2 times 5 raised to the 2 minus 3. Notice there are no parentheses here, but 2 minus 3 is clearly meant to raise 5 to that power. If you wanted to, you could think of 2 minus 3 as being inside parentheses, given the way it's written. 2 minus 3 is minus 1. Exponentiation receives priority. This is a negative exponent. 5 to the negative 1 is 1 over 5 raised to the first power. 1 over 5 to the first power is 1/5. We're now free to multiply 2 times 1/5 for a final result of 2/5, or 0.4. Our next problem asks us to solve for 2 times 5 inside parentheses squared minus 3. We need to resolve those operations inside the parentheses first. 2 times 5 is 10. Exponentiation now receives priority. 10 squared is 100. Now we're free to subtract 3 for a final answer of 97. Our next problem features solely division and multiplication, operations that have equal precedence, however are resolved from left to right if they appear on a single line as this problem. 24 divided by 2 times 6. The division operation is in the far left-hand side, so it receives priority. 24 divided by 2 is 12. 12 times 6 is 72. Our next problem is similar in nature, however it's been written differently. 2 times 6 appears entirely below the denominator. If you're thinking in a single line, one might think of this as 24 divided by parentheses 2 times 6 close parentheses. The operation inside the parentheses receives priority. 2 times 6 is 12. 24 divided by 12 is 2. The next problem asks us to solve for 100 minus 50 divided by 5 times 10. Again, multiplication and division are at the same level in the order of operations, and the operations proceed left to right. 50 divided by 5 is 10. Multiplication again receives priority. 10 times 10 is 100. Now we're free to subtract 100 from 100 for a final result of 0. Our next problem asks us to solve for 100 minus 50 inside parentheses divided by 5 times 10. Operation inside the parentheses receives priority. 100 minus 50 is 50. Multiplication and division are at the same level in the order of operations, and operations proceed left to right. 50 divided by 5 is 10. We're now free to perform the final multiplication. 10 times 10 is 100. Our next problem asks us to solve for 100 minus 50 divided by 5 times 10 inside parentheses. We need to resolve the operation inside the parentheses first. 5 times 10 is 50. Now division receives priority. 50 divided by 50 is 1, and 100 minus 1 is 99. Our next problem asks us to solve for 100 minus 50 inside parentheses divided by 5 times 10 in parentheses. Operations inside parentheses receive priority. 100 minus 50 is 50, and 5 times 10 is also 50. Now we're free to divide 50 divided by 50 for a final result of 1. Structurally, one can also think of this as 100 minus 50 on the numerator and 5 times 10 in the denominator. Again, 50 divided by 50 yields a final answer of 1. The next couple of problems are actually pretty difficult. We've got 27 raised to some operation, where again that operation could be enclosed in parentheses given the way it's written. The order of operation dictates that the multiplication on the left-hand side comes first. 2 times 5 is 10. Now we divide 10 by 15. 1 minus 2/3 yields 27 raised to the 1/3 power. This is a fractional exponent. Notice I've taken the trouble of enclosing 1/3 in parentheses. 27 to the third is essentially asking us the cubic root of 27. What number multiplied by itself 3 times yields 27? In this case, the answer is 3. Pay special attention when entering this into the calculator. If you enter this as 27 caret 1 over 3, the calculator evaluates this expression using the order of operations, where exponentiation comes first. 27 raised to the first power. Then it performs division. So 27 divided by 3 is 9. This is the incorrect answer because it's not the expression we wanted. If you want to solve for the cubic root of 27, you have to enclose 1/3 in parentheses. 27 caret parentheses 1 divided by 3 close parentheses yields a correct result of 3, the cubic root of 27. Again, the calculator always uses the order of operations. Check your work on the left-hand side to make sure that that's the expression you wanted. Lastly, we're asked to solve for the 7th root of 128, meaning what number times itself 7 times yields 128. The easiest way to do this on the scientific calculator is to raise 128 to the 1/7 power. Again, notice I'm enclosing 1/7 in parentheses. 128 caret parentheses 1 divided by 7 close parentheses equals 2. Why? Because 2 raised to the 7th power is 128. All right, hopefully that set of examples went well. Let's now discuss calculation using engineering prefixes and how to express the results in proper engineering format rounded to the desired degree of accuracy. All right, hopefully that set of examples went well. Let's now discuss calculation using engineering prefixes and how to express the results in proper engineering format rounded to the desired degree of accuracy. In the not too distant future, we'll soon put aside math for math's sake and be calculating electrical properties. This might seem a little confusing at first, given your prior knowledge of electrical circuit analysis. However, I'm asking you to just ignore the properties for now, and instead, concentrate on just the math and engineering format. One of the basic electrical properties we'll soon be examining is known as Ohm's law, where current through an element is equal to the voltage across it divided by resistance. Current is measured in units of amps. Voltage is measured in units of volts. Resistance is measured in units of ohms. Given known voltage and known resistance, can easily calculate current by dividing voltage by resistance. I equals V over R. For example, let's say resistor 1 has a resistance of 1.2 kiloohms. It's additionally known to have a 17.1 volt differential across it. Solve for current. I1 equals V1 over R1. Note R1 has a value of 1.2 kiloohms, i.e. 1,200 ohms expressed in the base unit. One must enter this value in the calculator with a proper indicator of magnitude. Enter 17.1 divided by 1.2 EE3. Press enter. The calculator returns a value in units of amps of 14.25 E-3. This is the calculator's way of saying 14.25 milliamperes. If we're asked to express this in proper engineering format, rounded to the tens place, this would be roughly 14.3 milliamperes. I don't want to belabor this subject any more than is necessary, so we'll wrap it up with these simple points of advice. Follow the order of operations, enter the numbers properly, and interpret and round the final results accordingly. 1.2 kiloohms is 1,200 ohms, and it is not 1.2 ohms. 1.43 milliamperes is 0.0143 amps, and it is not 14.3 amps. You must properly account for a number's magnitude using proper engineering format. Let's put your understanding of this concept to a test with this series of illustrated examples. Again, don't worry so much about the properties right now, but rather focus on the math involved and how to enter and interpret quantities using engineering prefixes. To help you out, I've included the units associated with each final answer. For example, problem 1 is an alternate permutation of Ohm's law, asking to solve for voltage in units of volts given known current in units of amps and resistance in units of ohms. Enter amps and ohms into the calculator using proper engineering format, and then just read the results in units of volts. Express all answers in proper engineering format, rounded to the tens place. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Our first problem is asking us to solve for V in units of volts, where V equals I times R. Enter this as 407.6 EE-3 times 171. Press enter. Expressed in proper engineering format, rounded to the tens place, V is equal to 69.7 volts. Our second problem is asking us to solve for R in units of ohms, where R is equal to V over I. Enter this as 120 divided by 30 EE-3. Press enter. Expressed using proper engineering format, the answer is 4 kiloohms. Our third problem asks us to solve for P in units of watts, where P equals V times I. Enter this as 690 times 24. Press enter. Expressed using proper engineering format, rounded to the tens place, P is equal to 16.6 kilowatts. Our next problem asks us to solve for P in units of watts, where P is equal to V squared over R. Enter this as 28.3 caret 2 divided by 4.3 EE3. Press enter. Expressed using proper engineering format, rounded to the tens place, yields a final result of 186.3 milliwatts. Our next problem asks us to solve for P in units of watts, where P is equal to I squared R. Enter this as 25.7 EE-3 raised to the second power times 1.2 EE3. Press enter. Expressed using proper engineering format, rounded to the tens place, yields a final result of 792.6 milliwatts. Our next problem asks us to solve for V in units of volts, where V is equal to the square root of P times R. Notice P times R are both under the square root operator. This means we need to perform the multiplication first. We can do this in two steps. 500 times 620. Press enter. Square root second answer yields a final result of 556.8 volts expressed using proper engineering format, rounded to the tens place. Our final problem asks us to solve for I in units of amps, where I is equal to square root P over R. Again, notice the operation P divided by R is entirely below the square root operator. It's again perhaps easiest to enter this in two stages. Let's perform P divided by R first. Enter 1E3 divided by 50. Press enter. Square root second answer yields a final result of roughly 4.5 amperes expressed using engineering format, rounded to the tens place. All right, we are just about done here. Before I let you go, I need your utmost attention regarding previous results as it relates to multi-step calculations. Often in the course of your studies, you'll be asked to solve for some property and express the answer using proper engineering format rounded to the tens place. Then, you'll be asked to solve for some other property and express that answer using proper engineering format rounded to the tens place. Then, you'll expect to use the results of these two calculations, or even 3 or 4 more calculations, to perform yet another calculation. Each result feeds the next stage, and if you use the rounded approximations, there's a loss of fidelity at each step. The key to avoiding this preventable disaster is don't use rounded approximations. Use the previous results. The point being, round the final answer, but use the most accurate representation of that quantity, i.e. the previous results, for the purposes of calculation. If you use the rounded approximations, your results will get less and less accurate the more rounded approximations you use. Allow me to demonstrate. For example, consider a 4-step sequence used to solve for power dissipated by an individual resistive element in a series DC circuit. We'll examine series DC circuit properties in greater details in later lectures. For now, just ignore the electrical properties and try to focus your attention on the math involved. You should notice how rounded approximations and previous results quickly diverge the further we get into the sequence. Step 1. Solve for total resistance. Series resistances add up. R total equals R1 plus R2 plus R3. Resistance is measured in units of ohms. Enter 390 plus 510 plus 430 and press enter. The calculator says 1.33 E3, which means 1,330 ohms using the base unit. If we were asked to express this result using proper engineering format rounded to the tens place, this would be roughly 1.3 kiloohms. Step 2. Solve for source current. Source current is supply voltage in units of volts divided by total resistance in units of ohms. Source current is measured in units of amps. We're presented with the first fork in the trail. We have a choice of using the previous results or the prior rounded approximation. Use the previous results. 12 volts divided by second answer yields an answer of roughly 9.0 milliamperes using proper engineering format rounded to the tens place. This is the correct answer. Using series circuit properties, we could say current through elements in series is the same. Source current equals I1, which equals I2, which equals I3. If, however, we use the rounded approximation of total resistance, we get an inaccurate, i.e. incorrect answer. 12 divided by 1.3 kiloohms yields an answer of roughly 9.2 milliamperes using proper engineering format rounded to the tens place. This is an incorrect answer. See where I'm going with this? We're only 2 steps into a 4-step calculation. We're already off the trail. It can only get worse from here. Step 3. Solve for voltage drop across individual elements. The voltage drop across an individual element in a series circuit measured in units of volts is current through that individual element in units of amps times resistance in units of ohms. V1 equals I1 times R1. We're again presented with another fork in the trail. We have a choice of using the accurate previous results or using the rounded approximation. Use the previous results. Walk up and grab the most accurate representation, i.e. the previous results for source current times 390. Press enter. This yields an answer of roughly 3.5 volts using proper engineering format rounded to the tens place. This is the correct answer. If, however, you use the rounded approximation of source current from our previous incorrect calculation, we get an increasingly inaccurate, increasingly incorrect answer. 9.2 milliamperes times 390 ohms yields an answer of roughly 3.6 volts using proper engineering format rounded to the tens place. This is a wrong answer. We are now 3 steps into a 4-step calculation and we're way off the trail. Step 4. Solve for power dissipated by an individual element. Power in units of watts is equal to voltage across the individual element in units of volts times current through the individual element in units of amps. P1 equals V1 times I1. We're again presented with yet another fork in the trail. We have a choice of using the accurate previous results or the rounded approximation. Use the previous results. Walk up and grab the most accurate representation, i.e. the previous results for voltage, times the most accurate representation for current. Press enter. This yields an answer of roughly 31.7 milliwatts using proper engineering format rounded to the tens place. This is the correct final answer. It's correct because we use the most accurate representation each and every step in the multi-step sequence, and we never lost any data along the way. If, however, we use the rounded approximation of voltage and the rounded approximation of current from our previous incorrect calculations, we get an increasingly inaccurate, i.e. increasingly incorrect answer. 3.6 volts times 9.2 milliamperes yields an answer of roughly 33.1 milliwatts using proper engineering format rounded to the 10th place. We have totally lost the trail and are deep in the blackberries. This answer, despite it following the same conceptual path as the other, is wrong. The reason it's wrong is because it used the wrong entries for every single calculation after step 1. In summary, even if you do it right, you'll get a still wrong answer if you use the wrong numbers. Here's my advice. Use the right numbers. Use the previous results. If that isn't enough to convince you, there's yet another valid reason to use the previous results. Not only does it yield a correct answer, it does so in less time than tediously manually re-entering incorrect data. Your choice, the correct answer in less time or the wrong answer in more time. In summary, use the previous results. You'll be glad you did. As a quick test of your understanding of this concept, I'm asking you to evaluate these two expressions and express your answer rounded to the 10th place. By all means, pause the lecture and try this yourself. If you're tracking, you should have gotten the following answers. 8 divided by 3 yields 2.7 rounded to the 10th place. 18 divided by 7 yields 2.6 rounded to the 10th place. Simple enough, right? Now perform the following calculation. 8 divided by 3 plus 18 divided by 7. Express your answer rounded to the 10th place. By all means, pause the lecture, try this yourself. If you're tracking, you should have gotten the following results. Spoiler alert, the answer is not 5.3. If you got 5.3, rewind the lecture and listen to the important points I made about rounded approximations and previous results. Never use the rounded approximations. Always use the most accurate previous results. Making use of the most accurate previous results, the correct answer to 8 divided by 3 plus 18 divided by 7 rounded to the 10th place is 5.2. I say again, never use the rounded approximations for calculation purposes. Always use the previous results. Not only will you get a correct answer, you will get a correct answer quickly. All right, that's about it for now. In closing, I'd like to remind viewers that while reasonable care has been exercised with respect to the accuracy of these lectures, I assume no responsibilities for errors, omissions, or suitability for any application or misapplication of their contents. Long story short, I'm going to dork up a calculation one of these days, and if I do, I'm going to do my best to issue a correction in the information and/or comment section associated with this lecture. If you do notice something there, please let me know and I'll do my best to correct it as soon as possible. In conclusion, this lecture presented a review of the order of operations, negative and fractional exponents, and the scientific calculator. I should level with you. If you feel incapable or unqualified to perform these skills without outside guidance, I am urging you to seek help instantly or turn back now. Electrical circuit analysis is taught with the language of numbers, and you must have a basic fluency to understand the contents of this series. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again in the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.